Hello, everybody. Welcome to our first round of Fellows Talks. Today we have two talks. The first up is Hubert. Hubert, whenever you're ready, if you want to get started.
Sounds good. Is it okay if I have my camera on?
Sure, no problem.
Perfect. All right. Hello, everyone. My name is Hubert Pugzlys, and I am sorry, did you say I could start right now?
Yes, yes, go ahead.
Okay, perfect. Um, so yeah, as I was saying, my name is Hubert Pugzlys. I'm a second year studying physics and computer science at the University of Florida. And for my fellows project, I worked on line segment tracking, GNN optimization. I worked under Dr. Chang, who's also here a professor at the University of Florida. And today I'll be going over some relevant background to my project, the project's synopsis, and then finally the findings of the project. So as you all are probably aware, the LHC is receiving a major update with the high luminosity project. During the HL-LHC runs, the instantaneous velocity or luminosity will increase the concurrent collisions per bunch crossing by approximately 350%. Now, what does this mean for the high energy physics community? With more collisions, we will receive tremendously more data for each run. And on the surface, this seems like incredible news as there's ample opportunity for new scientific discoveries and robust analyses. However, this amount of data also presents a serious challenge for the storing, processing, and analysis portion of the project. And as it stands right now, this will take an unprecedented amount of computing resources if we don't make any R&D developments. As you can see on the graph on the left, this can be clearly shown. If you look, the graph on the left shows the total CPU cost, resource allotment, and cost with respect to time. And the gray area shows the region where the possible range of computing resources for the LHC will be allotted over time. And as you can see, without any R&D developments, the computing resource cost for the LHC will exceed even the most generous of resource increases, which is why it is more crucial than ever to find ways to optimize this resource cost before the start of the high luminosity runs. Now on the graph, to your right, you can see the distribution of CPU resources under the HL-LAC without an R&D developments. And as you can clearly see, Rico and Rico Sim combined take up more than half of all the CPU resources used for the project. Approximately half of Rico and Rico Sim is track reconstruction, making it one of the most resource costly aspects of the project in terms of computing resources. If we are able to reduce the cost of track reconstruction, we would be able to most effectively reduce the overall CPU resource costs of the HL LHC and hopefully meet the predicted allotment for that run. Now, what is track reconstruction exactly? I'm sure most of you are aware what that is, but for anyone out there who isn't, particles collide at high energies and release many subatomic particles as a result. And these particles hit the CMS detector, producing hits that are stored as data. And track reconstruction is the process of taking all of the data and the hits in the CMS and, as the name suggests, reconstructing the tracks using algorithms to find the trajectories of these particles. And obviously, these trajectories can tell us a lot about the properties of the collision and what happened during the collision. Now, what can we do to reduce the resource cost of track reconstruction? One option, the option that we looked into, is parallelization. The algorithm that is currently used for track reconstruction searches for tracks in a linear fashion, making it more susceptible to combinatorics issues. As the amount of data increases exponentially, as it will during the HL runs, the combinatorics would increase exponentially, making the resources required for track reconstruction also increase exponentially. One solution to this dilemma is parallelizing the algorithm used for track reconstruction and employing the use of GPUs. A parallelized algorithm would reconstruct the tracks in a smaller, separated local bunches instead of linearly reducing the impact of combinatorics. In addition, GPUs have a more parallelizable structure, which is why we want to have GPUs employed. And this is beneficial because unlike CPUs, which are, as you can see in the graph, are plateauing in resource computing powers, GPUs are predicted to consistently increase in performance in the foreseeable future. This will allow us to more easily match the GPU computing cost increases with the allotted funding for each year. Now, with the relevant background out of the way, I will explain the project that I've been working on for the summer. My project consisted of optimizing a machine learning parallelized algorithm for line segment tracking. During my project, simply put, I wanted to find a function that takes the input of the information related to line segment tracking and then return 1 if it is likely related to a real line segment and 0 if it is likely related to a fake line segment. This function was approximated by a machine learning algorithm through a series of matrix multiplications performed during the training phase of the machine learning process. Now, the reason we're using machine learning in the first place is related to the matrix multiplications. I just mentioned that a parallelizable structure is more favorable due to the ability to use GPU resources. And as it stands, matrix multiplication is a commonly parallelizable structure computationally. Now, looking at the images in front of you, the graph neural network that I used would accept all the possible reconstructed paths seen in gray, and it would output the tracks, which are fake as seen in red and real as seen in yellow. One of the main objectives for my project was model optimization. To give a little bit of background from the machine learning standpoint, parameters are the configuration variables that are internal to the model, whose value can be optimized by the machine learning model itself, usually during the training phase of the algorithm. The graph on the right shows the increase in parameter count as a result of changing models' hyperparameters. Now, hyperparameters, on the other hand, are explicit external parameters that control the ingress, chain, and inference stages of the machine learning process. These hyperparameters are often managed, or were managed in our case by a .json file as seen on the right. And the goal of hyperparameter optimization is to optimize or attune the machine learning algorithm for the specific amount of and type of data that the model is using to a certain extent. And this improves the accuracy of the model for future applications. Some common hyperparameters include learning rate, simply put, how fast the model optimizes the weights, number of epochs, or where the amount of entire passage of the training data that the algorithm runs. And for this last one, I want to preface that the following hyperparameter is less of a hyperparameter, but is more akin to changing the structure of the model itself. But for the purposes of this presentation, I will refer to it as a hyperparameter. The hyperparameter that I focused on in my research was number of message passing rounds. This hyperparameter is found in many graph neural network models. By changing the message passing rounds, we are able to change the amount of influence that further nodes in the neural network can have on deciding individual line segments. The motivation of doing this hyperparameter or changing this parameter was because intuitively looking back to the CMS detector, we believe that the information from further nodes on the track can influence whether a portion of the track is real or not. In essence, we're taking a step back and looking at the entire track, allowing the machine learning algorithm to do the same in order to determine which tracks are real or not. Now for the findings of my project. This graph shows the raw curves for varying number of message passing rounds. A raw curve or a receiver operating characteristic curve demonstrates the performance of a machine learning model qualitatively. If the machine model performs better, it'll closely align towards the left and top side of the graph. And additionally, on the bottom right, you can see the AUC, or area under the curve, which is a more quantitative metric for this representation. And overall, as you can see, the NMP3 configuration performed the best. This table shows a comparison of certain selected values from the ROC curve. Comparing these values, we're able to see that the NMP hyperparameter optimization increases the model performance of a machine learning model by 3 to 12%. And now for a working rate, the increased accuracy is closer to 3%, but that is the given range. And then this is another visual metric for the performance of a machine learning model during the training phase of the process. This is the train loss with respect to epochs of training for completed for various message passing around values. And as you can see, the NMP3 had the lowest training loss, while NMP5 had the worst. In conclusion, the machine learning hyperparameter optimization of the model revealed that the message passing round of 3 produced the highest performing model based off of our data. This was slightly unexpected, as we predicted the more message passing rounds would be beneficial. As going back to the intuitive description, if we were able to look further down the track to the entire track, we expected that the machine learning model would also we'd use this information beneficially. But it turns out only about nodes that are NMP at NMP3 are useful for the track reconstruction process. Now, for future research, there are several things we want to look into. Optimizations of other hyperparameters could also be done. However, this isn't necessarily too big of a process because other hyperparameters can be all optimized fairly quickly through Bayesian optimization or some other optimization process during our project. As you can see on the right here is a score distribution for the NMP3 run, I believe. And while the orange curve follows a predictable pattern, the blue curve peaks on the very left. And this is not something we expected for our algorithm. And lastly, we want to be able to better compare the efficiency of the LST with the GNN track reconstruction. Since we have now a more efficient model for the GNN, our next step is to understand whether it truly does produce lower computing costs for the track reconstruction when compared to the original algorithm. And I think that's it for me. The rest are some additional slides. Thank you so much.
Thank you, Hubert. Any questions for Hubert?
Maybe if that's okay, I can ask a couple of quick questions.
Sure.
So Hubert, it was a very nice work. I hope you enjoyed that. I have a couple of just basic questions for me to understand a bit better the context. So is this done using CMS simulation of the detector expected at Illumi LSC? And do you know what process or anything was used to sort of for your events?
I hadn't dealt a lot with how we got the data, the inputs. I know it was through simulation work, but I couldn't tell you more than that.
That's okay. And do you know?
I apologize.
No worries. And then the other thing is sort of I don't know how much you looked into that. When you say that the true positive rate, right? It's in a lot of this machine learning application, this area under curve is a very used metric for good reasons. For us, in high energy physics, is sometimes a little bit of a deficient metric, mostly because in this type of application, you will never run in a situation where you want to have 10, 20% efficiency. That's true positive rate. That just is a failed reconstruction. It just, we can't run in that. There is no known use case for running in that type of thing. So that part of the curve is completely irrelevant to the metric. And so practically speaking, usually a good way to check is like putting yourself in the same true positive rate or false positive rate, like you've done in the table. And then comparing the actual efficiency or false positive rate. So that, I think, is a much better metric to figure out how well one setup does than with respect to the other. And I was wondering, do you have a reference also about how current algorithms are doing in with that metric in a similar setup, so that you have a reference sort of this method versus let's say the baseline or whatever has been used so far is doing?
Yeah, unfortunately, the problem right now is our GNN's machine learning results are not able to be fully generalizable or compared with the current algorithm that's being used, because I believe we focused on the outer tracks mainly of the CMS detector, so it's not the
okay, it's not easy to compare directly, basically.
Right. There's some constraints that prevented us, but that's part of our future work that I'll be continuing.
Oh, I'm happy to hear you'll be continuing that. Nice.
Thank you so much for your questions.
Thank you. Nice work.
Thank you, Hubert. Next up is Chris. Chris, you want to go ahead and share your screen?
Okay, good morning, everybody. My name is Chris Sellgren. I am a senior undergraduate student at UC Santa Barbara in California. And this summer I worked with Simone Pugzlys at Lawrence Berkeley National Laboratory on some studies involving a muon collider detector. So I'll start by just giving a short overview of the motivations for working on a muon collider. Basically, the history of high energy particle physics can be divided into two different types of experiments. There have been hadron collider machines and lepton collider machines. Hadron collider machines have been used to probe the energy frontier and get to higher energies for the beam, while lepton colliders, historically just electron-positron colliders, have been able to have a cleaner environment in which more precision measurements have been able to be made. As we're looking forward into the future of high energy physics and looking for a successor for the LHC, a muon collider provides a really beautiful potential for combining these two different fields. It overcomes that barrier between precision and energy. Because muons are so much heavier than electrons, they lose less energy to synchrotron radiation, which means that you can probe much higher energies while still having a cleaner environment. So there are a couple technical challenges with building a muon collider. One of the ones that set people back historically is that actually building the muon collider beam, building the muon beam is difficult. But as development has been made in that region, we're now looking at another set of difficulties, which is actually what happens on the detector side of it. So because muons in the beam are decaying, many particles are entering the subdetector that are coming from the beam itself, and we refer to this as beam-induced background. Here you can see a typical event. On the left is shown the type of signal that we would be looking for. So the green represents the small amount of hits that we would actually be trying to find, and then the red events are all the events from the background. So it really is like looking for a needle in a haystack. And so we're looking to try to develop algorithms that are basically going to be able to find what we're looking for. So one other thing I wanted to mention before we get started, a key part of actually registering out the hits is this process by which we take the interaction with the charged particle through the material and convert it into an electrical signal that we read out. And previous development in the Muon collider detector had been using a simplified algorithm for the digitization that was just extrapolating the geomet4 information and applying a Gaussian smear. But this summer, what I was working on was an algorithm that had a more realistic version of this digitization that incorporated the correct physics. So previously, this realistic digitizer that I mentioned had been developed, but it had been only applicable into one of the 6 subdetector elements of the tracker detector. So we have the vertex detector, the inner tracker, and the outer tracker. And we have this in what is called the barrel, which are the elements that are parallel to the beam axis, and the end cap, which are the elements that are perpendicular to the beam axis. And so what I did this summer was extend this from only being applicable into the vertex barrel into the inner and outer trackers, and also basically changing the algorithm to account for the geometry specific functionality to extend it to be able to work in the end cap. And this opened up a lot of possibilities for looking at various other effects. One of the other things that I discovered along the way in developing this realistic digitization was that there was a pretty serious bug in the way that the code was reconstructing the position of the hits. So what's shown in these plots is the distribution of the difference between the reconstructed hit and the true hit position that comes from the sim information. And what you see is before, the distribution had a spread of on the order of several millimeters, which is far too large and would have completely tanked any tracking algorithm performance. But after coming up with a new way of calculating the position from weighting the the individual pixels that were creating the cluster hit differently, I was able to reduce the spread in this distribution down to about 4 microns. Yeah, so the background that I was mentioning before, the finding the needle in the haystack, the main way that we do it is through these large-scale tracking algorithms. The issue is that in the Muon collider detector environment, there's just so many hits that feeding into the tracking algorithm takes way too long, and the algorithms are just too slow. So what we need are additional handles to be able to remove a large part of the hits that we feed into the algorithm before we actually run the tracking. Previously, there have been a couple ways that people have been doing this. One is through this idea of including this double layer where you have 2 thin layers right next to each other. And you can basically extrapolate where they're coming from really efficiently. The issue is that these are really difficult to construct and really expensive. And so we're looking at new models that are new designs for the geometry that don't use this double layer. One other thing that is really effective, though, is looking at the timing of the individual hits. So particles that are coming from the background have to travel a farther distance through material. And so we expect them to arrive a little bit later. And so by setting a cut on when we expect particles from the interaction point to arrive, we can remove a lot of the background, about half of it immediately. But another type of filter that we've been considering is this thing called the cluster shape filter. Basically, we expect particles that are coming from the interaction point to be leaving more hits, hitting more individual pixel elements if they are having a larger angle, as you can see in this first top left plot. So steep angles, more hits. Basically, there's a strong correlation between the size of the cluster and the angle that it's used to extrapolate back to the interaction point. Whereas, as you can see here, that a correlation does not exist for the background, which is on the left, where the distribution looks pretty isotropic. So this provides a really useful idea for a way that you can create a filter that will maintain a lot of signal while removing a lot of the background that we're not interested in. And what you can see here, this is a distribution, or this is a plot that shows the total number of hits normalized by the area for each individual layer in the subdetector element. And so what you can see is that the gray is all of the total hits. The blue is all of the hits after the the timing cut has been passed, and then the green and pink are after the timing cut and that cluster shape filter have been applied. And what we see is by applying these two different types of cuts alone, we can remove up to 95% of the background just by using the hit position and size of the cluster. Unfortunately, though, when we started applying this to the end cap, it wasn't quite so clean. As you can see here, the distribution for the background and the signal do not look drastically different. And by just applying these same types of cuts and trying to maintain greater than 95% of the signal efficiency, I was only able to remove about 20% of the background. So I had to come up with a couple more novel ways to design an algorithm that could cut out things more specifically. So one thing that needed to happen was, if you look back here, you can see that the cluster shape filter was only calculating the size of the cluster based on the amount of pixels that were hit parallel to the beam axis. But for the end cap, this needed to be extended to calculate the cluster shape in 2 dimensions. So I extended the cluster shape to calculate things more specifically. And another thing I saw was that when I looked at the difference between the signal and the background, there was a really distinct difference in the amount of hits that were left on different layers. So previously, all of the cluster shape filter was just incorporating the hits on all of the different layers. But I thought that by creating a new design for the algorithm that would basically differentiate the cut that was applied based on which layer it was, we could attack the background more specifically while maintaining a higher signal efficiency. So that's what's shown here. The left is the signal and the right is the background. And it's shown the different cuts that were implemented for different individual layers. So these are for the first and second layers. And as you can see, the orange and pink lines basically demonstrate anything above that is what we would remove, and anything below that is stuff that we would keep. And by basically just eyeballing this region and coming up with an initial set of cuts, I was able to reduce the amount of background that was retained by about 45% while maintaining greater than 95% signal efficiency. And this has really promising implications for the efficiency of the tracking algorithms, because if you're removing a large amount of the background that is leaving a lot of hits, it can seriously improve the amount of efficiency in the tracking. Another handle that I saw to potentially use in this regime was the energy deposition. What I noticed was that there were a large amount of background hits in the end cap that were leaving a large amount of energy deposited relative to the signal, and also creating really large cluster sizes. So hitting more than like 100 pixels at a time. This would correspond physically to something like a low PT electron, which is spiraling around in the end cap detector, leaving a number of hits. And these are the types of particles that are really going to slow down any tracking algorithm and really decrease its efficiency. So by adding a cut, for example, on a combined energy deposition and cluster size, we would be able to reduce the amount of particles that we have to feed into the tracking algorithms. Okay, so another set of things that I worked on this summer were just some additional studies on the digitization. A lot of the parameters that we've been putting into the digitizer algorithms are based on projections for where the R&D goals for the hardware will be in, let's say, a decade. But as we're trying to develop as the hardware is also accelerating, we also want to be able to understand what the effect would be if we didn't achieve those goals, or maybe got them to a different point. So I made a couple of studies to basically tackle these types of questions. One example of that is the timing resolution of the pixel detector themselves. So that timing cut that I was talking about really depends on how well we're able to get the precision of the pixel detector themselves. So what I studied here was basically how well that timing cut would be effective at different resolutions of the pixel detector. And what I saw was that while increasing the digitizer resolution by pretty linearly would remove the amount of, it would pretty linearly decrease the effectiveness of the timing cut. The cluster shape filter was effective enough that basically the cluster shape filter alone could do the equivalent of buying you twice as bad of a resolution in the timing resolution. Another area I studied was the effect of changing what's called the readout threshold. So the readout threshold are basically the number of electrons that need to pass into a detector element to register a hit. So previously the benchmark that had been used was 500 electrons, but what I showed here was that this could be safely increased to about 700 electrons without substantially decreasing and actually perhaps even increasing the accuracy of the reconstructive position. Another thing that I studied was how the cluster shape filter would have an effect on removing signal particles that were not originating from the interaction point. So the cluster shape filter uses the angle information, which extrapolates back to the interaction point. But for particles that might travel some distance before decaying, they might be at risk of getting vetoed when they were actually signal particles in the first place. So what this showed was basically how the signal efficiency varied as a function of how far away from the interaction point a particle would be created. And then the last set of studies I did was basically extending these types of studies to a new geometry. So previously, all of the Muon collider detector studies had been done assuming a 3 tera-electron volt beam. But there's new development that's been done on basically looking at what it would be like to use a 10 TeV beam instead. What's really nice about increasing the energy of the Muon collider beam is that although the particles are more energetic, and thus leave like a larger shower and even a larger background, they last longer because of the time dilation, and so there's fewer particles that are actually decaying in general. And to the first order, these effects cancel, and so you're basically able to increase the energy without significantly scaling the background. However, that doesn't necessarily mean that the backgrounds have a similar shape. So as you can see here, although the total size of the background in the 3 TeV and 10 TeV case is pretty similar, that looks like the 10 TeV case is much more central in terms of where the angles at which the background particles are entering the detector. And unfortunately, this means that the cluster shape filter would lose effect in the 10 TeV case. However, if we look at the timing at which the particles arrive, what we can see is that in the 10 TeV case, the particles are arriving at drastically different times than they are in the 3 TeV case, which has the potential to change the effectiveness of the timing cut. So when you combine these two effects together, what you see is that versus in the 3 TeV case, the cluster shape filter is pretty effective, and the timing cut is relatively less effective. In the 10 TeV case, the timing cut is significantly more effective, while the cluster shape filter is less effective. However, in the end, it comes out to they're both reducing over 95% of the background, and in the 10 TeV case, we may be even reducing about 98% of the background from these two cuts alone. Just a quick summary of the things that I talked about. This summer, what I worked on was the digitization of the Muon collider detector tracker. So I found a bug in the way that positions were being reconstructed and adjusted the algorithm for the realistic digitizer to handle support for more of the subdetector elements. I used this new realistic digitization to extend the cluster shape filter to new regions, namely the end cap, and came up with a new way of calculating the cluster shape filter to remove a significant amount of the background. I did some smaller studies on individual targets for R&D goals, and I studied the effect of what it would be like in the 10 TeV geometry environment. In the future, there's still a lot of work to be done in this field. A huge area of focus would be to how these handles on the background could be used to study the actual effect on the tracking performance. And there's a whole bunch of other studies that can be done on tracking in this regime. So that's a summary of what I did this summer. And here are some references if anybody's interested in looking at the original, but like any of the code or anything like that, that's all here. But that's all I have. So thank you so much.
Thank you, Chris. Nice talk. Any questions for Chris? I see your mentor. Your mentor's connected. Simone, do you want to say anything about Chris's work?
Yes. No, actually, wanted to take the occasion definitely to thank Chris. I think it was an extremely productive summer, and I think even Chris sort of undersold that the amount of work that he had to do to having to deal with DD4HEP's geometry classes and the physics of the digitization that he had to understand to really dive into that code. So he did an extremely great job, I think. And it's nice that you managed to focus on the results and the presentation as well, because he also had time to produce those. So I'm really happy that he joined us for this summer, and I'm also happy that he got excited about the project, and hopefully we'll continue to work on this.
Great. Sounds like it was a great experience. That's what we like to hear. So that's all we have for today. So thank you all for coming. Thank you to Chris and Hubert for your presentations, and there's more to come. So bye.
Bye-bye.
Thank you so much.
Thank you so much.